Now we get to learn some shortcut differentiation rules. So we're going to do the derivative of a constant multiple of a function, the sum of two functions, and the difference, and power function. Let's start off with the constant function. So f of x will equal some constant c. So you set up the limit definition, f prime. Here's your difference quotient. But f is a constant, so f of x plus h is c. F of anything is c. So f of x is c also. C minus c is 0. 0 over h is 0 everywhere, so the limit is 0. So the derivative of a constant equals 0. And you can see that on the picture, that if f of x is a constant, then it's a horizontal line which has slope 0 everywhere. Now let's move on to constant multiple. So this rule says that if a function is a constant times another function, then its derivative is going to be constant times derivative of the first function. So that one is proved this way. So g prime of x, it's the limit of c times f of x plus h minus c of f of x over h. Factor out the c to here. Then factor the c in front of the limit, because a limit of a constant times something is a constant times the limit. And you just have the difference quotient of f there, which the limit as h goes to 0 gets you to f prime. So the derivative of a constant times f prime is a constant times f prime. We use that rule a lot. Then we come to the sum rule, which says that the derivative of a sum of two functions is the sum of the individual derivatives of the functions, and a difference is similar. The way this works is h of x is f of x plus g of x. H prime of x is therefore f of x plus h plus g of x plus h, and then minus f of x plus g of x. And you can see that all we do is move some things around, and we're going to end up with the f function set up in a g. Then we're going to divide the h into both quantities. We're going to get the difference quotients of both. The sum limit rules tell you that you can break up the sum of the limits. So then you just have the two derivatives summed together. So again, that rule is the derivative of a sum of two functions is the sum of the individual derivatives. Now we go on to powers. And this really comes in handy when we do derivatives of polynomials. So if f of x is just x to the n, we want to figure out what the derivative is at. So we have f prime is equal to the limit definition, and you have x plus h to the n minus x to the n over h. So you realize you have to know something about x plus h to the n. So we pause right there for a second and we go over to the famous Pascal's triangle, which are the red numbers here. Pascal's triangle is for the expansion of a binomial. And as you can see, if you do this one, x plus h to 0, well, that's just 1. X plus h to the first, well, that's just x plus h, but notice it's a 1, 1. X plus h squared, if you square that out, you get 1x squared plus 2xh plus 1h. Notice the configuration of 1, 2, 1. X plus h to the third is this quantity here. Notice the configuration of 1, 3, 3, 1. And then lastly, the x plus h to the fourth to see the final, the whole pattern here. Has a configuration of 1x to the fourth, 4, 6, 4, 1. But notice what's happening in each case to the x's and to the h's. Take a look at the x's. The x's right here is x to the third, x squared, x to the first, x to 0. Here it's x to the fourth, x to the third, x squared, x to 0. So the second term, which is very important, always has 1 degree less, and it's the one with 1h there. Always. Look at this term here. These right here. Okay? So, following that pattern, now let's just figure out, for example, what is the difference quotient using x to the fourth. So here it would be divided by h. And then it would be the expansion of x plus h to the fourth, which is all this, minus off the x to the fourth. So those x to the fourth would cancel out. And they would, on all of these, any x to the end, the front running term would cancel out. You'd have the Pascal's triangle for the second term right there. That would be the pattern. So the h would divide into every term here and would produce this expression after you divided the h in. Take a look at that. And then as h went to 0, because there was no h in the front term, there was no h there, that will survive. All the other terms have an h. And so they will all get knocked off as h goes to 0, and you're going to be surviving with the 4x to the third, which is that second term in from the left on the Pascal's triangle. So I think you can see that if you were to continue this on, then this whole difference quotient and the limit of that would just turn out to be n, whatever the power was, x to 1 less power. And that is your famous power rule for derivatives. So, for example, if you have f of x equals x to the 6th, then f prime of x is just going to simply be 6x to the 5th. But this, you always have to know why it's happening. And this over here, this Pascal's triangle, and this development is the reason.